next speaker we're going to hear from is Choe from Carnegie Mellon, who's going to talk about some very interesting work on multi-level optimization.
Thanks for the introduction. And my name is Sang, and today I'm going to talk about systems and applications of multi-level optimization. This work is a collaborative effort with Willie, Pengpao, and Eric. So I'm going to start the presentation by asking this question. So what is missing in current machine learning? I guess like Professor Kunze also talked about causality as one of the things that we're missing in current machine learning. But another thing that we're missing is the interactive learning scenario. So if you think about the current machine learning, if you're like given the task like image classification or the like machine translation, what they do is basically finding the patterns in data to solve the task, and there is basically no interactions with other agents. But in human learning, as shown in the below figure, let's take a let's consider the school interactive learning experience. Like for example, teacher gives homework to students, and then given this homework, students try to solve all the homework and update their knowledge. And then after finishing homework, students take a test. Then teacher evaluates the students' performance in the test, and if they are not performing well, they also update the homework to give a better experience for better learning experience for students. So by interacting between this teacher and students, they make this teaching and learning experience more efficient and helpful. But we're not the social science workshop, we're at the machine learning workshop, so we want to understand this from the machine learning perspective. So if you take a closer look at this scenario, so from the students' perspective, their main goal is basically solving all the homework problems. And in doing so, they also update their knowledge. And also from the teacher's perspective, their main goal is basically improving students' test score by designing a better homework. And then in this case, what teacher does is basically updating the homework. So if we approach this scenario from the machine learning perspective, these green parts, the solving homework problems and improving student test score, is kind of very similar with the optimization objective, like the loss function. And then the orange part, update knowledge and then update homework, are very similar with the parameter update stage in machine learning. So basically, teacher and students are solving the optimization problems, but the unique characteristic of this scenario is that these two optimization problems are interacting through these red and blue arrows. And now we want to kind of understand this scenario, the interaction between optimization problems, a little more formal way using some mathematics. And that's where multi-optimization comes into the play. So multi-level optimization basically refers to a problem where we want to solve the nested optimization problems or the hierarchy optimization problems with two major criteria. The first one is the lower level problems are constrained by the current solution of the upper level problems. If you consider the previous scenario, the lower level corresponds to the student, and then the upper level corresponds to the teacher. So the students are trying to solve the optimization problem given the homework from the teacher. And then teacher, which is upper level, the second criteria, the teacher is constrained by the optimal solutions from the students, which is the knowledge students gained after solving all the homework, and then try to improve the homework designing, constrained by the optimal solutions of the students. So if you look into the middle equation, so the blue part is basically the upper level constraint, and then the red part is basically the low level constraint. As you can see, upper level constraints are the non-optimal solutions, and then the low level problems are the optimal solutions. So in this way, we can formulate the interactive optimization problems more formally using multiple optimization framework. And there are actually multiple ways to solve this multiple optimization problem, like Bayesian optimization, as really presented earlier today, and like evolutionary strategies. But in this work, we want to focus on the gradient-based multiple optimization. This is because in the current deep learning era, a lot of optimization problems are really high dimensional. And then those used are the optimization methods like Bayesian optimization, evolutionary strategies, oftentimes fail to scale to this kind of large high dimensional problem. So in gradient-based multiple optimization problem, we want to basically calculate the gradient for each level. And then this gradient can be decomposed into two parts. The first one is the direct gradient part, and then the second one is the indirect gradient part. The reason why we want to consider the indirect gradient part is because our optimization problem is constrained by the optimal solutions of the low-level problems. But then these low-level optimization, the optimal solutions from the lower-level problems can be a function of the current level parameter theta k. For example, in the previous teacher-student example, student solution is constrained by the teacher's current homework, theta k, theta 2. So L1 is basically a function of the theta 2, and we want to take into this account when calculating the gradient. And even though we had just two agents in our previous example, in real scenario, there can be actually way more complicated interactions between multiple agents, and that can be all formulated using by recursively applying the chain rule as in the below equation. So to perform the gradient-based multiple optimization, what we basically need to do is computing the below equation. And there are actually several challenges in calculating this equation. The first one is the computation complexity. We are dealing with the really high dimensional problems. And then these red and green parts, which is called best response Jacobian, can be like millions by millions if we are considering like the million size, the millions dimensional problems. So computing this million by million metrics, or even saving this millions by millions metrics is computationally and then from memory perspective really expensive. So what we notice is that the rightmost term is vector. So instead of doing the matrix multiplication, by performing matrix and vector multiplication from right to left, we can reduce the computation complexity from cubic to quadratic. And now that we are doing the matrix vector multiplication, what we basically need to do is recursively performing this matrix vector multiplication with best response Jacobian. But then here, there is another problem because now we want to differentiate through the optimization. For example, in student-teacher example, we want to differentiate the outcome of the student's knowledge with respect to the teacher's homework. And then differentiating into optimization is really not straightforward. So we normally use the technique something called like iterative differentiation or implicit differentiation. But as you guys have already noticed, I guess a lot of people haven't even heard of these terms in their life. So one of the difficulties is definitely programming mathematical proficiency in understanding what is iterative differentiation is, what is implicit differentiation is. And then another issue is that usually in this iterative differentiation or implicit differentiation, they usually calculate the second order gradient like Hessian information or the multiple forward vector propagations. That means that you're using way more compute and then the memory than the traditional training. So we also have to deal with this memory and compute bottlenecks even after understanding all the programming and mathematical details about those algorithms. So, but no one wants to do this. So that's why we decided to develop our multiple optimization library, Betty. So what Betty does is basically doing all this gradient calculation automatically. And then also we also added a lot of system support like distributed training and mixed precision training to solve the memory compute bottlenecks. And then also we provide a modular programming interface for various algorithmic system design. For example, there are multiple algorithms for iterative differentiation or the implicit differentiation. We let users to choose whatever algorithm they want using just one line of code change in our library. And in doing so, we wanted to democratize multiple optimization and let users model the various interactive learning scenario in an easy way. So here's some examples of our code. So basically, so there are two major components in Betty. The first one is the problem class, and then the second one is the engine class. So in the problem class, we define each level's optimization problem. How do we do that? It's very similar with the PyTorch Lightning. We define the loss function, and we provide the module optimizer data loader, and then that's it. That's like how we define the optimization problem for each level. And it's very similar with PyTorch Lightning. So I guess most people, one won't have any problems in learning this kind of framework. And then the second one is the engine class, where so in the previous problem class we defined the optimization problems, but in the engine class we define the interactions between the optimization problems. And how we do it is basically using the Python dictionary. So we have upper levels and lower levels, and then there are two types of interactions. One is upper to lower, and then the other is lower to upper. We define these kind of interactions using Python dictionary, upper to lower and lower to upper. And we just pass these dependencies into interaction dependencies into the engine class, and then finally user just run the engine that run, and everything will be automatically taken care of by the API value. Yeah, so that's the systems for multiple optimization we developed called Betty. And there are actually a lot of cool applications of multiple optimizations, like meta learning, hyperparameter optimization, neural architecture search, reinforcement learning, adversarial learning can all be formulated as multiple optimization. For example, in adversarial learning, attacker, and we have two agents, attacker and defenders, and they're interacting with each other. Reinforcement learning, we have like multiple agents and then environment interacting with each other. Hyperparameter optimization, we have hyperparameter and the main network parameter interacting with each other. We can all model these kind of things using our framework Betty. But in this presentation, we specifically want to focus on automated data preparation application. The reason why is because I guess a lot of you guys may have heard of this already before. Like 80% of the data science test time is basically spent in data collection, organization, and cleaning. And it's just not about the data scientist productivity. Also, like 75% of the data scientists report that the most boring and the least enjoyable part of their job is basically this like data cleaning, data collection, organization. So we decided to ask this question: can we automate this part by cleaning this like noisy and imbalanced data automatically? And then that's where multiple optimization comes into play. So we again borrow the teacher-student example here. So we have teacher who re-rates and collects the data, and then the students basically solve, try to learn from the noisy and imbalanced large training data, but re-rated and then corrected by the teacher. And then after finished learning, students take a test on small clean validation data sets. And then if the student's performance is kind of poor on the validated data set, the teacher updates their re-rating and correct mechanism. And we just like iterate this procedure like multiple times until students really perform well on the clean validated data sets. And then after that, we can kind of say that because students is performing well on the clean validated data set, we can kind of safely say that the data is correctly clean. So this problem can be basically formulated as an extended bi-level optimization problem, where we have two optimization problems on the second level and then one problem on the first level. The second two problems on the upper level is basically label correction, then the data re-rating, and then the bottom level problem is like whatever problems that the data scientists have. So thanks to our library Betty, we were able to really clean. Make the program interface really simple for the users. So basically what users need to do is providing the model optimizer, optional linear scheduler, and then data loader. And then they just, again, train and run. And then it will automatically do the data cleaning by doing label correction and data aggregating. And this is the performance we get. So we first, tried our algorithm into cloning 1 billion data sets. This is the web crawl session data with the 1 million data points. And then the noise ratio is approximated to be like 40%, and the imbalance ratio is like 5 to 10. In addition to this large dirty data, we additionally constructed 7,000 clean small validated data set. Compared to the 1 million data points, 7,000 is even less than 1% of the whole data. And after performing the automated data cleaning by the label correction data re-rating, we observed the performance improvement of like 7% in absolute scale, maybe like 10% in the analytical scale. Just by cleaning less than 1% of the data. And then that was the image classification task. And then we also tested our model of the text classification example as well. So a lot of people these days use like weak supervision from Snowflake AI for generating training labels very quickly. But because of the nature of the weak supervisions, the labels are usually very noisy. So this is the first row basically shows the label accuracy generated by the weak supervision algorithm. Like it's like the lowest one is like 50%, and the highest one is like 84%. And then unfortunately, we have the access to the gold labels for this all these data sets here. So the second row performance basically shows that the performance we get from training our model on the gold labels. So we can, this is kind of the upper minimum we can achieve with these data sets. And then the baseline performance is basically the performance we get from training our model on the noise data. And as you can see a lot of like performance degradation for all the data sets. And then the final is after applying our data cleaning algorithm. Approximately, I guess, 10%, so the validation size is about 10 times smaller than the training data set for all these tasks. And just by collecting 10% of the data, we were able to recover the full performance, the gold performance for almost all tasks. So that being said, now we don't have to spend a lot of time including training data. You only need to spend like 10% or even like 1% of your time including the data, and then guide your, and using this clean validation data set, we can guide our training by reweighting and then correcting the data. And actually we can add more strategies like data augmentation or data invitation. This is some of our future work. And yeah, so this is something that we're trying to build on like data-centric analogs platform in the future. And another thing that's really nice about this framework is that we don't touch anything about the model and then the loss function here. But once you have like a working model for your business, people are kind of really reluctant to change their model of the loss function. But we are only dealing with the data parts here. So people would be more willing to, and you know, like changing the data is like, you know, it happens all the time. People think that they should clean the data. So changing the data, people has no mental barrier. But like changing the model and loss function, they may have a higher barrier. So that is really nice part. And then we make this process really cheap by only allowing users to, you know, play around with the validation data set instead of the large training data. Yeah, so yeah, that is the end of my presentation. Thank you.